Range. Welcome you all to this class of canal design, which we'll be continuing today. We started on canal design yesterday, and we'll be continuing with this class today again. What we were discussing on canal design, let us just recapitulate. We started with the very fundamental concept of design of channel, and then at that point we did discuss that channel may be line canal or it can be unlined canal. Well, now when it is line canal, then we could see that the problem of scouring or say erosion is not there. As such, our design concept is different, or rather we try to make the channel in a most economic way. And then when we talk about unlined canal, then our problem are different. There it can be non-alluvial, the channel, I mean within the unlined category itself, there can be non-alluvial channel or the channel can be alluvial channel. Well, when it is non-alluvial channel, then again we could see that problem of erosion is not there up to a certain limit of velocity, and problem of sedimentation is of course not there because we consider that in a non-alluvial channel the sediment carried by the water is less, and as such the sedimentation problem is not there. However, the erosion problem, as I said, that it is not there up to a certain limit, then we should maintain up to that limit of velocity. That means our design principle become such that we should decide our shape, we should design our shape of the channel, we should design our size of the channel in a way that the flow velocity does not exceed that permissible limit. That is maximum permissible velocity concept come there. And when we talk about alluvial channel, then the problem can be both scouring, that is the erosion of the bed and bank, and the problem can be of sedimentation. So that way, we just need to take care of both and it is very difficult to have analytical solution for such problem, and then generally people try to have the channel of the size so that a velocity is achieved which is referred as critical velocity. That critical velocity is that this velocity or under this velocity the channel will neither be eroded nor there will be a deposition, so or sedimentation. So that sort of critical velocity how we can have, that is again a very challenging task, and for that purpose generally empirical relations are used, means the equation derived on the basis of lot of observed data of such stable channel that are used. And of course, some semi-empirical theory are there, like track force method, and that are also applied. Well, and in the last class, we could see that design principles are different for different type of channel, and design principle for line canal is to have the best hydraulic section, and we started with the design of a rectangular channel, and then we could complete up to trapezoidal channel. Well, then again we tried to see that in trapezoidal channel the design criteria is that or the best hydraulic section is that one where the length of the side channel, length of the side slope is equal to half of the top width. That was the condition that we could derive. And using that condition, again, we can see that for a trapezoidal channel, when it is the best section, best hydraulic section or most economic section, it is satisfying this particular condition, what we have stated, then it can be found that hydraulic radius R for that situation is equal to half of the depth. That is R is equal to Y by 2. And the same condition we could see for a rectangular channel as well. And in rectangular channel, the condition for most efficient section we are using several terms, a most efficient section, best hydraulic section, or say most economic section. In fact, all are meaning the same thing, that is the perimeter minimum. And for rectangular section, we could see that B, that is the bed width, is equal to twice that of the depth. So that was the condition for best hydraulic section. And of course, we have already explained what is the condition for trapezoidal section. Now let us see what will be the condition for triangular section. We'll start with that. Well, now let me take a triangular section. Well, say this is a triangular channel and this is the depth of flow. And let me just call this angle as theta. And of course, we can just give idea about this theta in terms of the side slope also, that is z:1. It can be written as theta or z:1. And depth of flow in triangular section is say y. Okay. Now let us see what is the expression for area. Area is equal to half of the base into altitude. Now what this base is basically, as we know that this top width is equal to z into y this much, and again z into y this much, because depth is 1. And so this top width we can write as say twice z into y, twice z into y. So our expression for area is half of the base into altitude. So this is what the base, and altitude is y, and I mean this height is y. So that is equal to zy square, and that will lead us to an expression for y is equal to root over a by z. Well, as now we know that our concept of making a design for most economic section is that we will try to make the perimeter minimum, that is P. If we get an expression for P, we will try to make P minimum. And in that case, earlier we were doing dP dy, that is with the change of y, how the P is varying, and we are trying to see that when dP dy is equal to 0, that will give us the expression for minimum value of P. Now here we can see, of course, y we could change, but if we change the z, if we flatten the z, if we bring the z here, depth will automatically come down, or perimeter. So for a given area, if we change the z value, depth will come down. If we increase the depth, if we reduce the z value, it will be coming like this. Rather, if we increase the z value, it will be coming like this. If we decrease the z value, it will be going like this. And then the depth of flow will be changing, and then perimeter will also be changing. Weighted perimeter will also be changing. So we can see, and for design of a triangular section, what we can specify, that suppose we are asked to design a triangular section, then we can specify that, well, this should be the area and this should be the side slope. Once we specify the side slope, because here B we need not specify, B is not coming at all. So B means bed width I am talking about. So we need to specify the side slope. Well, so we can see that when P will be minimum in terms of Z also, there is a variation of P perimeter with respect to Z, we can say. So we can try to find what is dP dz, and that way we can try to equate this to equal to 0. So this way, let us see what is the expression for P, and perimeter P. Let me write the expression for perimeter P. That perimeter P is equal to, say, this length is equal to y root over 1 plus z square. That means this part is root over, say, this length is, if it is 1, it is z root over 1 plus z square. So this will be, this total length will be, for one depth it is like that, for y it is root over, say, 1 plus z square, and then we'll have to multiply it by y. So this is the perimeter, and this perimeter This is only one side. So, but we have perimeter means we have both the side, this and that. So it will be equal to 2 times of y root over 1 plus z square. And that can be written as 2 times of this y now we will be expressing as root over a by z. And then we can write this as root over 1 plus z square. Well, and this can be written as again, say if we take this z inside this sign, then we can write it as twice root over a and root over 1 by z plus z. Well, now to have this expression in a simple form, we can square the both sides. So squaring what we can have, squaring this equation, squaring the above equation, what we can have, we can write this as p square is equal to, say, 4a then 1 by z plus z. Now we can do differentiation of this equation with respect to z. So differentiating with respect to z, what we will be getting, this is, say, twice p, then it is dp dz, and our interest is that this should become 0, is equal to 4a, and then this expression will become this dz is equal to 1, and this will become, say, minus 1 by z square. This will become minus 1 by z square. Well, if dp dz equal to 0, so dp dz equal to 0 implies, now from this expression what we have, so this is 0 means, this left hand side is 0 means we have that 4a 1 minus 1 by z square is equal to 0. And now in a channel, if area is 0, there will be no flow. So the question cannot be let area, whether area will become 0 or not. This is a product of this and that item. So this term cannot become 0. And as such, this expression must be equal to 0. And so this implies that 1 minus 1 by z square is equal to 0. This implies 1 by z square is equal to 1, and 1 by z square can be equal to 1 only when z is equal to 1. And z is equal to 1 means what we are getting indirectly, that our z is equal to 1, 1. So this z is equal to 1. That means this angle theta, the angle theta must be equal to 45 degrees. So this implies theta is equal to 45 degrees. So a triangular section will be the best section when we can have theta is equal to 45 degree. Or theta 45 degree means when we talk about the total angle, then this is equal to 90 degree. So a 90 degree channel, we can say 90 degree channel means the angle of the triangular section should be 90 degree for this is to be most efficient. And of course, in practical situation, when we propose triangular channel, then it may not be possible to provide exactly a triangular channel, and then in many a time it is given like this, and this portion is rounded up, and then we provide these things like that. But the angle, if we extend, this should be, say, 45 degree and 45 degree like that. Well, then we can go to the another type of channel, that is circular channel. Okay, in circular channel what will happen, say, let me draw a circular channel. Well, say this is the center, and then say flow is, we are considering that flow is up to this level. Okay, this is the at this level, and then this length is equal to radius. Means we are, suppose the radius of this circle is r. So this is r. And in both the direction, this will be r. And let me draw a normal in this direction, and this angle is theta. Well, now you can concentrate into the slide that how we can write that area. Area is equal to, well, this entire area, our fluid is actually, or the water is in this portion. So how we can find this area? We can find the entire area. Entire area will be basically, say like for the whole circle it is pi r square. That means twice pi is the total angle, so half of the pi r square. And for this sector, we know from our very basic geometry that it will be theta into r square. But from that theta into r square, we will have to deduct this triangular portion. We will have to deduct this triangular portion. And this triangular portion, what will be the length that we can have? Yeah. This is r, okay, this is theta. So what this length is basically, say, we can have, this is r sine theta. And what about this length? It is the height of this is r cos theta. Okay. Now having this, we can write that flow area or sectional area of the flow, is as theta into r square minus, again we can go to half of base into altitude, so half, and base is r sine theta is this portion, so it will be twice r sine theta, and altitude is r cos theta, so we are writing r cos theta. Well, this can be written as theta r square minus, say, r square by 2, and why I am writing this 2, I am not cancelling at this point, because twice sine theta cos theta we can write as sine twice theta. So this part we are clubbing twice sine theta cos theta, sorry, I'll have to leave this also, twice sine theta cos theta as sine twice theta, and then we are having this expression. Well, that can now be written as, say, r square by 2, and then we can write twice theta, this twice theta because 2 we are bringing out, minus sine twice theta. Well, this is what the expression for area. Now expression for perimeter. Here perimeter is this length. Okay. So this is what perimeter. And as we know that area, perimeter, or say perimeter of the entire circle is twice pi r. That way here the perimeter of this portion will be, say, twice theta r. Here our angle is this one. Okay. So perimeter P is equal to twice theta r. So these are some of the fundamental expression that we are getting for area and perimeter for a circular section. Well, now let us again come back to the concept of best hydraulic section. Now what we mean by best hydraulic section, again the same thing, that is minimum perimeter. So, but one point here is that for circular section, the most efficient section is considered from 2 different angles. Well, what that 2 different angle? That is, one point is that we want to maximize the discharge. Till now, in all the section or in all different type of channel shape, we were talking about the best hydraulic section is that which can carry maximum discharge. But in case of circular section, we consider from 2 different aspects. One is that maximum discharge concept. One is maximum discharge. And the second is, say, maximum velocity, maximum velocity. Why? That is, in many cases, these circular sections are used vacuum pipe and for different practical purpose. Sometimes it become necessary. And what more important point is that discharge through this section, if we come to this part or say we are trying to find what the discharge is, then in many a time our objective is to have maximum discharge to the channel, and in many a time our objective is to have maximum velocity through the circular section, so that we can avoid siltation in the channel. And so that way, and in circular section, maximum velocity and maximum discharge is not the same, is not providing us the same value. Or say other section, when it is area is constant, we are having that discharge is equal to A into V, that we are getting. When area is constant, when discharge is maximized, means velocity itself is maximized. But here it is not like that. And that's why from two different angles we look into the condition, and it is found that from both the point we get little bit different expression for the efficient section. Now from maximum discharge condition, if we go by the maximum discharge condition, say we will be getting Q is equal to area into velocity, and this means